So thank you for having me here. It's been an intense but very pleasant week. And so my name is Gianna Cauzzi. I come from the National Solar Observatory in the United States. And the idea was to give you an overview of the modern solar research, what we do nowadays and why. And also at the end, I talk about why we still go around the world and chase eclipses, at least from the solar point of view. I know there are other people here that are chasing eclipses for rather other reasons. So my talk is meant for a scientific audience, but not an astrophysics audience. So I hope that I found the right balance in presenting. And I'm always too long. If you think things are boring, you do this, and I understand. Okay. There. I think that modern solar research could probably be divided in three big topics. The first one is that the sun is a star, even if we don't remember that very often, right? But since it is very close, we can study a lot of things in detail, and that can serve as a template for many other astrophysical environments, other stars, but also other physical mechanisms. And I'll be talking mostly about that. The second one is plasma physics, particle acceleration, magnetohydrodynamics, and so on. The sun shows us interaction between plasma and magnetic field and radiation at scales and energies that we cannot access in our laboratories. So there is that aspect, and I will just say just a little bit of that. And then finally, the space weather. You might have heard that term, which is the fact that the magnetic activity of the sun causes phenomena that might have, sometimes do have, direct repercussions on Earth and so on our life, and especially on technology. And again, I'll say something a little bit about that. So I want to start from the beginning. Kenny already said something last week, but the sun is a star. And I think I like this diagram that we call Hertzsprung-Russell, because it's one of those plots that's very dense in information. So if you go, the x-axis is what we call the color of a star, that is, how much blue the star emits versus how much red, and is essentially a proxy for temperature. So on the left side, you have the very hot stars, 10,000 Kelvin, 20,000 Kelvin or so. On the right side, you have the very cold ones, 2,000, 3,000 Kelvin surface temperature. On the y-axis, you have the total luminosity of the star. So here you have the brightest, and here you have the dimmest stars. And if you look at where the plots go, they don't go everywhere. They're not scattered everywhere, but they cluster themselves. And I only wanted to talk about this. Can you see the cursor? Yeah, sort of. All about this, which is called the main sequence, which is the place in that diagram where the stars that are in their main life phase, when they are producing helium from hydrogen in their core via nuclear reactions. So up here, you have certain mechanisms to do that conversion. Down here, more like a sun and so on, you have different nuclear chain reactions and so on. But the idea is always the same. You go from hydrogen to helium, and as you do that, you emit energy. Right? So the sun is here, and it's sort of an average star. It's in reality a little bit brighter and a little bit hotter than the average star if you count stars, because there's a lot more red stars, small stars than the blue. So normal. Indeed, if it weren't so normal, probably we would not be here, because there would not be the conditions for life to exist on our planet. I just put down some numbers. The radius of the sun is 700,000 kilometers, which is 100 times Earth, more or less. The distance is 150 million kilometers, which we call the astronomical unit. The mass is essentially all the mass of the solar system, 98%. Jupiter is the other big one, of course, and then all the rest. The luminosity is 3 in 10 to the 33 erg per second. And if I did the numbers right, this is of the order of 10 to the 13 more than what we as a species needs. So that's a lot. And the sun rotates. That's an important one. It rotates around its own axis, which is not straight with respect to the ecliptic, where we rotate around the sun, so there's a little bit of a tilt. It rotates on 27 days, but it's important to remember that it rotates differentially. The equator rotates faster than the poles, and that's important as we will see. So it's a very average star. The fact is, it is very close with respect to all the other stars. To date, I think we can resolve the surface of a few stars, maybe 2 or 3. Betelgeuse is one, but we see few pixels, right? I mean, this is the sun, and we see it in all the glory details. And so this is a movie that zooms us in onto the surface of the sun, and this is the kind of features that you would see at high resolution. So if I go back, this is probably something similar to what you saw yesterday in the telescopes or the day before, right? That's one spot, single spot up there. But then you zoom in and you see that the spot has a very fine structure. It's very dark in the middle, and it's not black. It's just emitting less than the surroundings because the sunspot is colder than the surroundings. It's about 2000 Kelvin colder than the surroundings. And I think I will say why in a little bit. And it's got all these things that we call penumbra, fine structures. We can look at it even closer. The previous movie was from a telescope in space that is 50 centimeters in diameter. This is from the newest NSO telescope. It's a 4-meter on the island of Maui in the Hawaii Islands. And so you can see details that are even finer, right? This is again a spot. I think I put the scale here, 30,000 kilometers more or less. So what looked completely dark in the other image, here you can see that actually the inside of the spot is not just a monolithic thing, but there is a lot of other features that come up that are actually convective cells. And again, I'll get to that. I think that this is a little movie. So the field of view, if you go in much detail, the field of view cannot be big. So this is just the spot. This is a penumbra, and here a little bit of light. And I don't know if you can see this little smudge here. That's the state of Sinaloa, just to give you an idea of the scale. Right, so it's not dirt on the slide, but it's the size of the state of Sinaloa. I always like to put this in context. Right? Anyway. So, and another thing that I need to say at the very beginning, and if you remember this one at the end of the talk, I would be happy, is that astronomy does science mostly via spectroscopy, the analysis of the light, which is emitted by stars and cosmic sources. We do have planetary missions. We have, say, sample return from asteroids and so on, or we have probes that measure magnetic field in situ, somewhere in space. But mostly we do analyze light. So astrophysics, most of the time, does not measure anything, but it infers the physical property of bodies from the light that they emit. So you always have to go through some sort of model, because you have to say, okay, if I have plasma, this density, this temperature, this whatever, and the way to emit light is this, then this is the spectrum I get out. So that is always the case. Right? It's never measured. It's an inference of things. So we like to say measure because it's easier, but it isn't. So this is the spectrum of the sun, and I don't want to say too much because tomorrow there is a talk on irradiance. So this is the emission intensity versus wavelength, and this is the visible, the rainbow colors. This is what you see at Earth. You see all these dips here because our atmosphere cuts a lot of the emission of the sun. And this is what we see with our eyes. Then you're going to the UV that we have to go to space to see. Here, the infrared and radio we do from Earth. If you expand the spectrum, and this has been known since the mid-1800s, not only you have this continuum emission goes from blue to red following this curve, but also you have these dark lines that are called absorption lines, which are the fingerprints of elements in the atmosphere of the sun. If you have a certain absorption line at a certain wavelength, you know that there is that kind of element in that ionization state that is doing that kind of electronic transition. So the lines are, again, I mean, the continuum is one, but also the lines are one of the main tools for our spectroscopy analysis. And these are called the Fraunhofer lines because they were observed by Mr. Fraunhofer back in the 1800s. If you disperse this once more, for example, this, where am I? These are the lines of sodium that are used, for example, in the street lamps. That if you disperse this even more, this is what you get. You know, there's a lot of spectral lines in the solar spectrum. And again, our experiment was to be done in the blue, which we didn't because of the clouds. But this was the range where we would work. And these two here in the yellow are the two sodium lines that I was mentioning. Okay, so studying the light emitted at the surface plasma models, we have an idea of how the internal structure of the sun is. And so we know that there is a core where the nuclear reactions take place, which is about 50 million Kelvin, and it's pretty dense, of order of 150 times the water, the density of water. So that is where the energy is released. Then the energy is transported towards the outside by radiation, this darker red area. It's called the radiative zone. It goes all the way to about 70% of the radius. And so there the photons are absorbed, re-emitted, and so on. And slowly they change their frequency. You go from very high energy photons, gamma rays that are emitted in the core, to something of lower energy. Then conditions change for the sun and solar-like stars. And the energy is actually more efficient to be transported by convection. Convection is like you have a hot surface in the bottom, and you heat up and things, you know, rise and then eventually cool and come down. And so this is the convection, like a pot of boiling water. And that is called the convective zone, which is very important because the motions in this zone determine the presence of a magnetic field, like we observe. Finally, you get to the surface, what surface of the sun, which is defined as the envelope, the film around the star, where the plasma becomes transparent to radiation, so it doesn't absorb it anymore. You know, just below it, you don't see, really, there is no light coming from there. The place where the light comes from is called the surface of a star. And from there, it goes on to interplanetary space, and we can detect it and intercept it and so on. And that is the photosphere with a temperature of order 5,700, 6,000 Kelvin or so. And it's not a rigid surface. It's not like the surface of the Earth. It's very, very tenuous, right? The gas actually is, the density is probably several thousand less than the density of this air now. Maybe I'll just skip this and just mention that we have ways to study the interior of the sun, even if we don't see it, by measuring motions at the surface of the sun, using a technique that is similar to seismology, you know, earthquake science. You see how sound waves propagate, and you can infer what kind of temperatures and densities you're encountering. You know, the Earth seismologists know if there is hard rock, melted rock. I don't know, I'm not an expert. And we do something similar for the sun. And so we know that the sun rotates in the convection zone differentially. So the equator goes faster, about 25 days, than near the poles, which is about 30, 32 days. We also know that the beginning of the radiative zone rotates like a rigid body. So you can imagine that here at the interface between these two things, there's a lot of shear. And that's important because it's where we believe the dynamo, the mechanism that gives rise to the sun's magnetic fields, that is where it operates. Although this is not by any means established. I know there's a lot of people that still think that the dynamo is created throughout the whole of the convection zone, not just in that thin interface region. So the idea is that in most of the sun, plasma and magnetic fields are frozen in. That is, it's mostly, the plasma is mostly ionized, right? And so charged particles are forced to go along magnetic field lines, and vice versa. The frozen in condition means that depending on energy density, if the plasma wins, the field goes with the plasma, or if the magnetic fields win, the plasma goes with the magnetic field, right? So inside the sun, the plasma wins, there's a lot of it, there's a lot of matter and mass. And so if the plasma rotates, the field goes with it. And you remember the equator goes faster. So if you have these field lines, the field becomes stretched and stretched and stretched, and that amplifies it. And eventually you get some very strong field that become buoyant, they rise, and eventually they emerge at the surface. And they emerge as sunspots, what we saw with our own eyes, right? Those are sites of very intense magnetic field that are emerging from inside. Then the full dynamo requires that this mechanism sort of goes back and you start another cycle, again, with weak fields, mostly this direction, and then slowly become, the whole cycle is about 11 years. This was, I don't know, I'll just go there. I like it. This is an instrument of NSO, again, it's called GONG, that observes the sun continuously because it has 6 stations throughout the world. So they, day and night. And so these are all the sunspots that emerged last year in 2023. I thought that I liked that very much just because it's a fun movie to watch. You can see many things. There is many spots because we're next to the activity maximum. The spots emerge in 2 bands. They don't emerge at the equator, but in 2 bands of latitude. They don't emerge at the pole. These are all constraints that any dynamo model has to take into account, right? And the dynamo models nowadays are, again, pretty good. There is still some intrinsic chaos in the system that makes it difficult to have a very deterministic approach to this problem. Okay, and finally, how do we know that really the sunspots are the site of strong magnetic fields? And again, we say that we measure, actually we infer. We know it because certain spectral lines, if they are emitted by a plasma that is under the influence of magnetic fields, they behave differently. It's called Zeeman effect. There are others, but this is the principal one, the main one. So you see, this is there is like a slit that goes through the spot here. And if you disperse the light, you see that the spectral lines stay here, are this wide. The spectral lines in the spot are much wider because you have extra components. And they have also a certain pattern of polarization. That's what we use to infer the magnetic field. And for example, this is again yesterday. On the right, what we saw on the telescopes. On the left is the magnetic field at the surface. And so you see there's a lot of structure, even where you don't see spots, for example. Places like this, there is no clear sunspot, but that's an active region where we have magnetic fields of a certain intensity appearing on the surface. Okay, this I'll skip, and this is just a view to show you that the cycle exists. This is solar cycle 24, which is the one that finished, the complete one. So you go from the minimum 2008 through the maximum 2013, and then back again, right? 11 years of magnetograms, just as an example of. Okay. So now we move a little bit from the interior outside towards the atmosphere of the sun. And again, let me go back to the photosphere that I have already introduced. So the red is the same spectrum that I showed you before. The yellow is what is measured outside of the Earth's atmosphere. And the black curve is a black body curve. I don't know if you are any familiar with black body. Never heard. It's a very common concept in physics. So a black body is a system where you have matter and radiation that are in equilibrium with one another. And if you leave it undisturbed, if you could peek, if you had a little hole in there and you could look at the radiation that's emitted by a black body, this would be the curve, the black one would be. And it depends only on temperature. So hotter bodies will have higher emission and the peak would be further to the blue. And colder bodies would have lower emission and the peak will be further to the red. And one thing that they always remember, these curves do not intersect. So the blue ones are higher and they go that way. The red ones are lower and they go this way. Anyway. So that's very useful because it allows you to do a lot of approximations that work very well with the photosphere. The photosphere has a certain extension of 500 kilometers, more or less. And you remember the radius is 700,000. So it's very thin, very thin. Temperature already said, the density I already said. So it's a very tenuous gas, even if it is a black body. We've talked about sunspots already. But sunspots are not there all the time, right? We know there is a cycle. So during the minimum, for example, what do you see? Well, this is something you see all the time and everywhere on the sun. And the sunspots disturb this pattern. This is called granulation. You see all those little blobs, some dark and some bright. So these are the remnants of those convective cells that we were discussing before that bring energy all the way to the surface of the sun, essentially. And indeed, I don't have it here, but if you would have a movie of velocities, you will see some go up and some go down. The brighter are hotter, about 500 Kelvin hotter, and the darker are colder. With our new telescope, this is a recent movie, and you can see it in more detail. Every one of these blobs is about 1,000 kilometers. And this is about, I think, half an hour of evolution, just to, it really reminds you of something the bubble felt, no? I think we can safely say that we do understand granulation very well. It's a fluidodynamic effect. It's not very difficult. It's conservation of mass and momentum. Mass that goes up has to come down, and it goes up, it cools, and it goes down. It heats up again, and so on and so forth. There are still reasons to study at higher definition. For example, these brighter things, ribbons that you see in between blobs, those are the sites of intense magnetic fields. They are as intense as sunspots, but they are not dark because they interact differently with the convection because they are so small. And so that's a very modern topic of research. The other topic of research is that convection and granulation occurs on all solar-like stars. And maybe you don't know, but anyway, an important part of astrophysics today is the search for planets around other stars, the exoplanets, we call them. And you need very precise measures to find them. And the granulation is a source of noise. So characterizing it well is important to sort of be able to kill that noise and be able to find to be more sure that you are finding planets around other stars. Let's go up. So let's go above. The atmosphere or the sun, like that of Earth, is gravitational stratified. And so as you go higher, your density goes down, and we go to a place that we call the chromosphere. And the fact of the day is the chromosphere is a name that means sphere of color, and it comes from eclipses. Because if we were fast enough yesterday, for a second or two, just at the beginning of totality, you should, if you have good eyes and the sky is clear, you should have been able to see a red ring around the moon. And that is the chromosphere. It's red because it emits mostly in a spectral line of hydrogen, which is in the red. There is a little less emission in another line of hydrogen of the same series, which is more towards the green, so it becomes kind of purplish. But that's what it gets its name. And it is also the source of these things. Many of you have seen them and have pointed them out, these sort of blobs that were red, and you could see them, that they were red, right? Or at least the camera could see them. Those are chromospheric features, and I will describe in a second. And in an eclipse behind that white ring, that is the corona, and we go. So the chromosphere is much less dense, like 10 to the minus 10 to the 7 times less dense than the photosphere. The extension can be as short as 2,000 kilometers or as high as 5,000 kilometers. It's a very dynamic environment. And it is very dynamic because it's very tenuous. Every kind of input to it has a very large reaction because the density is so low. The important thing is that the temperature is of order of 10,000 Kelvin. And you go, hold on a second, the surface is 6,000, and as I go away from my main source of energy, it becomes 10,000? How does that happen? That is a lot of research that's going into that. And it ties, the chromosphere and the corona all tie together. The chromosphere is not a black body. It's two atmospheres. And by the way, this is a picture of yesterday from a friend of mine from Minnesota that was in Texas. If you can look at it in a little more detail, on the right, I'm sorry it's not red, but I think that it is red. So actually this was taken in a chromospheric line that is in the blue. So if you look at any quiet time, this is what you see at the limb of the sun. You know, you have all these features that go up and down and they wave around and so on. And that is what would make for that small ring of red that you would see around at the time of totality. The bigger blobs that we saw yesterday are something like this. Now, I think this is a few hours, are called prominences, and they form, you see them here in this corner. Those are, again, the things. And one of the problems that we have nowadays, we still do have it, is how can something which is dense, then sort of dense, and cold, 10,000 Kelvin, be inside the corona, which is super hot and not dissolve immediately? You know, how do they maintain their stability? That is matter of research as well. Okay, so, and for the chromosphere, we have many lines in the visible that we can use, and if you go and look at them, you see that the magnetic field starts to have an effect. Very, very strong effect, in the sense that the features that you see, and we know because we can sort of measure it, they do follow magnetic field lines. You have a lot of these elongated, we call them fibrils, but you know, we have a lot of terms. And you know, they seem to go along the field lines of the magnetic field. So the chromosphere is a situation in between the photosphere and the corona. The photosphere, the plasma wins. In the corona, as we will see, the field wins. Here, sometimes we do, sometimes we don't. So, and that makes for a lot of interesting effects to study of non-equilibriums. So now we go to the corona. That again, you speak Spanish, and you know, corona means crown, or that is. And again, the term comes from eclipses, because it was seen as this white thing and all around the sun, the surface of the sun. So again, this is a picture from yesterday from one of the students from CU Boulder that went to Illinois, Carbondale. They had better weather. And so we saw maybe something like here yesterday, you know, like the beginning of the corona, but they were able to see more of this extended. So the corona is even less dense, again, a factor of 100 or more. And the extension is as much as you want, essentially, because, you know, after what we call the corona, historically, then it becomes the middle corona, and then it becomes, I don't know, the solar wind, and then it becomes the heliosphere. It's plasma that keeps going out from the sun. And the temperature, characteristic temperature is a few million Kelvin. And again, problem, how is that possible? But one thing that needs to be clear is that this is not an energy problem. We have plenty of energy to sustain the chromosphere and the corona, because all those motions in the photosphere are more than enough, a factor of 10,000 more than enough, because the densities in this upper atmosphere is so small that really you don't need much. It's just a matter of why does it become so hot in that point at that time, right? And what's the mechanism that does that? And absolutely, the corona is not a black body. Since it is so hot, it emits well in the UV and X-rays. We provided an X-rays, and we have this satellite that's called SDO, it's a NASA satellite that continuously sends us down images, a full disk of the corona at different wavelengths. On the left, in red, there is a helium-2 emission line at 30 nanometers, characteristic of 50,000 Kelvin. In the middle, the yellow, it's an iron 9, so very ionized element, characteristic of about 1,000,000 Kelvin. And on the right in blue is an iron 16, so even more ionized, That's characteristic of 2.5 million kelvins. And I don't know if you remember, maybe not, because I've shown a lot of images, but the places where you see a lot of emission in the UV are where you have strong magnetic fields. So the magnetic fields is certainly a fundamental component of this heating of the outer solar atmosphere. We have many mechanisms, magnetic waves, you can excite them very well, but they don't dissipate, so I don't know how they can hit where we want it to hit. We have magnetic reconnection. The magnetic field sort of simplifies itself when it's very tangled and then release some energy there. And again, this is things that people are working on. Okay, so hold on, let me go back because I wanted to stop a minute. Okay, this is a star, right? Like the sun, many other stars have the same thing. So you say, okay, fine, but why do I care, right? I mean, the first one is that it's a very interesting problem, physical problem, and how does this happen? It might have ramification into astrophysics. And so, but the other important problem is, the other important reason is that these places where we have a lot of coronal emission are also the places where often we have what we call eruptions and explosions. We call them flares, coronal mass ejections, and so on. And those might have a direct effect on Earth. So this is a movie again from SDO. Let me stop it so I describe it. So it goes from the magnetic field to the coronal emission at higher temperatures, and it shows where one of these magnetic explosions happen. And you see that there is enhanced emission in all those wavelengths. And let's see. So it happens here. And so you see that thing becomes brighter. And this is a 1 million Kelvin. It becomes brighter here. And then again and again. You get the drill. The fact is that these things emit, a big flare emits about 10 to the 33 ergs, which is what the sun emits in 1 second, right? But this is a small area, so it's a very powerful event. But the important thing is that it emits mostly in the UV and X-ray in terms of radiation. And those come to Earth in 8 minutes. And those are ionizing radiation that can change our own atmosphere, in particular the ionosphere. So it changes the number density of electrons in the ionosphere, which then has repercussions in, for example, communication, GPS and radio waves. And actually, the effect of solar activity on radio waves was first noticed during World War II, when the Americans realized that it was a very large activity period. And so there were a lot of disturbances and things. And there was, for a while, the idea that the Germans maybe were doing something to scramble communication, right? And instead, it was solar activity. And after World War II, Air Force was heavily involved in solar research, mostly for this reason, that they are the ones that funded NSO, for example. So we come from military money. The other thing that you might have noticed is in some coronal lines, for example, this one, you see emission, extra emission in the flare. At some point nearby, you can see some areas going very dark. And that is because mass has been ejected from that place, has been expelled. So there is less mass and it emits less. And that is what we call coronal mass ejections that might have even worse repercussions on our own technology and planet. And again, this is a bit of a slow movie. I think it's up here. It happens hours or so. You see a flare going on there, upper left. And then about an hour or so. Oh, that's a slow one. Okay, there you go. That thing is ejected. That was one of those prominences that we saw before, that at this point is so destabilized that it is expelled into space. And some are big, some are small, some are really big. And if you go on the SDO website, you can see all sorts of them. And if you have something in space that looks even further away, you can see them, right? This is a spectral line. This is the white light, like the pictures of the corona that you saw yesterday. It's colored red, but this is the same thing, right? It's just essentially the intensity of these things tells you the density of electrons. That's in the extended corona, because that is light which is it's photospheric light scattered by the electrons. And so there's I think it's several days. So if you look at it a bit, there is ejection all the time. And again, this is something that was not so well known until we sent coronagraphs to space, which was maybe 30 years ago by now. You know, we knew they were there, but not so many. We didn't expect them that many. Sometimes they come to Earth, right? They are ejected in all directions. So sometimes Earth is in the right position to be directly hit by one of these guys. It depends, of course. They are charged particles, and so they propagate along the magnetic field again. And so there needs to be a certain configuration of where this happens versus where the Earth is. And so this is an artist's rendition of what's happened. So you all know that the Earth has a magnetic field, and that protects us because the particles will be forced to propagate only along magnetic field lines instead of coming straight to Earth. The idea is that when you have this big blob of mass with its own magnetic field, there could be some restructuring of this system that will accelerate particle, and they will penetrate Earth through the poles, magnetic poles. This happens on the day side. The strong events actually happen from the night side. It's actually the magnetotail, the place where most of the electron acceleration occurs. And so then you have, again, the precipitation, and then you have these things that are called aurorae that you probably heard about, that I've never seen one. I would love to see one. And they are beautiful. They're really beautiful. But we care about them because all of this can be very disruptive. Because you have mass that comes in, you have currents, strong currents, because those are electrons that are moving. That's a current, right? And so you have interference with communication, aviation passenger safety problems. You can have transformer problems that are hypercharged by these currents. They can propagate along, especially in the northern regions, the pipelines for oil that lead to corrosion. And so they live less than they should, and so on and so forth. So this is the whole system of what we call space weather, and that's why a lot of people are interested in solar activity and why flares and explosions occur, where they occur, and when they occur. The overall idea would be to be able to predict them. We are not there yet. Okay, so this was just a slide with all sorts of instruments that we have, and we have a lot. Especially NASA has a big fleet of instruments around Earth and away from Earth. We have a probe that's orbiting the sun. It's got very close, like 10 solar radii, and that is an in situ. It measures the field and the particles velocity in situ of the solar wind there. This is our 4-meter telescope in Hawaii. This is the other NSO part of that 6-station network that I was talking about, the GONG. And finally, we come to eclipses. How are we doing with time? Okay, I try to be fast. So eclipses. Why do we still need to study them? You know, we have a lot of satellites that can study the corona up in space and so on and so forth. Eclipses, well, first of all, they're beautiful, as you've seen. That is, I think, one reason enough. But eclipses allow you to have the clearest view for now of the extended corona. And so this is just an example for show. And I need to remark that these are heavily processed, right? This is not what you see with your eyes. Here you need a fantastic, good camera, an excellent photographer, and somebody which is really good with image processing, and to show all these intricate details. If you look at the corona from the ground on a normal day with an instrument that we call a coronagraph, so essentially it's a telescope that has a disk that holds the sun. This is the best you can do, more or less, right? For the full. And the problem is that, yes, your telescope is caught in the disk, but the Earth's atmosphere is there. And the atmosphere scatters the light that comes from the sun. So the noise that introduces is of the order of 10 to the minus 6, if you're lucky. in terms of photospheric intensity. And your signal is maybe 10 to the minus 4 if you're really lucky. So you understand this is a signal to noise kind of problem. During an eclipse, the noise becomes 10 to the minus 9 because the light is blocked before it enters the atmosphere, right? The moon is doing it for us. There is still some because it comes from the other side of the totality path, but it's certainly much. So that's why eclipses are still so good. And from the space, you have no atmosphere. Of course, the scatter is not there, but it is more difficult to send up a telescope which is big enough and precise enough to be able to do this. So, I mean, it's still, I would say that the efficiency of the process of observing eclipses is not very high because then it's cloudy and other things and so on. But people are doing some good things. Historically, scientific things were, well, first of all, finding out that there is a corona, 1750 sketch of the corona, the first photo in 1850. The helium as an element was discovered during an eclipse. It was never observed before. There is an emission line which is very close to the sodium lines in the yellow. There was another, this was in 1868. In 1869, there was a new element that was discovered that was called coronium that emitted in the green. It was very strong emission. It took 60 years or so to find out that coronium does not exist. And that is a line of a very ionized iron. It's actually iron 14. So it took a lot of development of atomic physics and quantum mechanics to understand, what kind of transition was the one giving rise to this spectral line. And so that was done in 1939. So this is iron 14, as we have seen the highly ionized iron emits in the corona very much. One very good result that came out of eclipses is a proof of general relativity. And the general relativity states that where you have a very heavy mass concentrated body, the space modifies, changes. And so the light travels along that modified spaces. So the idea was you have a certain star field that should be seen like so. But if the sun is in the middle and you see the stars, the light coming from those stars goes through a different path and you would see them in a different place. And indeed, that is what happens. And that is what was proved by Eddington in 19. Yeah, this was one of the best results from eclipses. Modern, there are a few dedicated groups that really make a living of studying eclipses from the ground. And, they're very successful. For example, they can study incredibly thin details of the interaction between the chromosphere, the prominences, and the corona surrounding them using spectroscopy and very good imaging. As you can see in these pictures, this is a prominence, that's the corona around it. Again, how does this 10,000 Kelvin body survive in the super hot environment? I'll skip this, it's too complicated to explain. Another thing that people do a lot is trying to construct global models of the solar magnetic field. You remember the sun rotates, and at any given time, we see half of it, right? Because it's a disk in the sky. And so if you want to do a global model, you would need to know what is the field also on the other side, but you don't. So they have certain ways, they sort of take time and they wait for the sun to rotate a certain amount so that they have a good view, but it's never instantaneous, right? So this is now, but this part of my field map was taken 2 weeks ago, and this was taken 2 weeks from now, or something like that. So, but they do. And this is an institute in San Diego that does this a lot. They predict the shape of the corona, of the wildlife corona. And this was their prediction for yesterday's eclipse. And I haven't found yet anybody with a good image of the extended corona in white light. And so this is the only one I have. And I don't know if I can compare or not. Also because the one on the right, I suspect still has not been rotated. You remember the sun is inclined. And this has the solar north straight. This might not. So take it as it is. But just to get an idea of what people are doing. What we wanted to do was to look at the spectrum in the blue, as I mentioned at the very beginning, because all these electrons that are in free electrons in the corona, they do scatter photospheric light. And since they are very hot and they move, they smear the photospheric spectrum. They broaden it and sort of hide all the features of the spectral lines, right? So, but at this wavelength, and at this wavelength, there are two very big assertion features in the solar spectrum that somehow survive this mechanism of smearing. And by looking at how deep, so look just only at the solid curve here, by looking at how deep these things are and where exactly they happen, you have a sense of the temperature and the motion of that particular feature in the corona. And it is a complementary way to find temperature, and so with respect to spectral lines. And it can be better at times because you have to use certain assumptions for spectral lines that might not be true, equilibrium and stuff, and so. And a version of this experiment, not by us, will fly on the ISS hopefully next year. It said 2023 as the upper limit. It has not started yet, so that's what happens with that. Somebody last week asked about citizen science, and there has been, I know of several, I put here only two. One is called CATE, Citizen CATE, that stands for Continental America Telescope Eclipse. The idea was to have a network of 40 or plus stations throughout the path to obtain images of this kind, so to create a movie of 60 minutes or plus, to study, you know, variation of density, flows, and so on of this extended corona that we still don't measure very well. I don't know how successful it was. Our colleague Dave Elmore, that was here with us next class yesterday, he was the first CATE node because he was all the way here, but he didn't get much. So I don't know how these people fare. And the other one was, I think it was mentioned on Friday, it was a sun sketcher. This was an app created by a group of people, again, sponsored by NASA. And the idea was that everybody looking at totality could record it with this app on their phone and then send the data to NASA. And with millions and millions of data points, their goal was to get a very precise determination of the shape of the sun. The sun is not a perfect sphere. It's a little squeezed at the poles because it's a rotating, not rigid body. We know the shape to a certain precision. They wanted to do better than that, to the 1 part per million precision. I think I'm finished. Taking picture, okay. And I wanted to thank you all for, you know, this very intense week. You've been fantastic hosts. And really, I don't think we could have asked for anything better.